Hello, welcome to the channel Microwave Testing. Today we will learn about a method which is well known from medical diagnostics, but it is also used in non-destructive testing of parts and materials samples. This method is called nuclear magnetic resonance, NMR. We know a special variety of NMR from medical diagnostics. There it is called MRT for magnetic resonance tomography, or MRI for magnetic resonance imaging. NMR uses the interaction of strong magnetic fields with electromagnetic waves with frequencies which range from some megahertz up to more than 1 gigahertz. So they well extend into the microwave region, which ranges from 300 megahertz to 300 gigahertz. And so we can call NMR also as a method of microwave non-destructive testing. In the following weeks, we will see application videos for NMR in non-destructive testing. But today we will start with a more introductory video. So let's start.
Nuclear magnetic resonance. You are more familiar with this term than you may think. You've probably heard of magnetic resonance imaging, or MRI. That is a technique that is used in hospitals to acquire images of the human body. And MRI uses the principles of nuclear magnetic resonance, which is the topic of today's video. Hello and welcome back to my channel. I'm Maria Bias, and in today's video we will learn how radio waves are used in a technique called nuclear magnetic resonance, or NMR. We will start by exploring the types of instruments that are used to acquire NMR experiments, and then we will move on to learn the general principles of NMR. And if you stay until the end, you will get to see the large variety of NMR applications in many different areas of research. So let's start exploring NMR together by first having a look at the instruments that we use, and we will start with one that you might have already seen or heard of, the MRI scanner. You might have seen this kind of MRI scanners in movies, or you might even have had the experience of getting an MRI scan in your own life. This is the most common use of NMR outside of research. In the medical field, MRI is used for acquiring images inside the human body. And to acquire the images, we make use of very large superconducting magnets. Just a side note here to clarify superconductivity. A superconducting material is a material that transports electrons without any resistance. And we'll talk more about it when we'll see what the magnet looks like on the inside. So now let's get back to the magnet. In this picture, what we call the magnet is the big cylinder on the left. The patient, resting on the patient table, is then sent into the magnet to acquire the images inside the body, like the brain images we see here on the right. In research labs, we use magnets similar to the ones used for MRI, but with a few differences. And before we get into those differences, I should clarify here that in order for these magnets to work, they should be inside a lab. Usually they're in the basement of a research building, and they should be connected to other electronics and to power supplies. Moving on to the differences between NMR and MRI magnets. First, usually in NMR, our magnets stand vertically, and the sample, which is much smaller than the human being, is placed in the magnet from above or from below the magnet. Second, the magnets we use in research usually have higher magnetic fields than those used in hospitals. And third, as I hinted earlier, our samples are much smaller and they can be prepared as either liquids or solid samples. If we work with liquid samples, we hold the samples in these kinds of tubes, and that's called solution state NMR or liquid state NMR. In solid state NMR, the sample is a fine powder that's placed in an NMR rotor like this one. They are very small cylinders with a diameter varying from 7 mm to 0.7 mm, and they are shorter than around 2 cm. Whether the sample is a powder or a liquid, the NMR tubes and rotors have to go inside the magnet, and they are placed in what we call probe heads. These probe heads contain the radiofrequency coil, which we use to send radiofrequency pulses to the sample, but we'll get back to this a bit later. If we look inside the magnet, you'll see that in the center there's a bore, and that's where the probe head goes. The sample is then placed inside the coil that's in the probe head, and that is placed inside the magnet. And the magnet is illustrated here as a very large coil. And that's exactly what the magnet is. It's a coil made of superconducting material. That means that as long as the material is superconducting, it conducts electrons without resistance. And the continuous circulation of electrons then creates the magnetic field. So how do we keep the material superconducting to ensure a constant magnetic field? We keep it cold. Very, very cold. We have to keep the superconducting coil in a bath of liquid helium, which you can see in this drawing as the light gray area. The temperature of liquid helium is 4.2 Kelvin. That is minus 269 degrees Celsius or minus 452 degrees Fahrenheit. Like I said, that's cold. One last thing to mention here is that there is also a liquid nitrogen dewar that surrounds the liquid helium dewar. This acts as a buffer between the very cold temperature of the liquid helium and the room temperature where the instrument is kept. This is done in order to slow down the liquid helium from boiling off and having to refill it often, which is a problem because of the high cost of liquid helium and the scarce helium resources. Some of the newer magnets no longer use liquid nitrogen, but have a system of liquid helium reliquefaction, thus reducing the need to refill the magnet with liquid helium. Now that we're familiar with the NMR instrument, let's see how does NMR work. For that, we'll have a look at nuclear spins, what they are and what they do when they are placed in an external magnetic field. Let's take a look at the hydrogen atom, for example. We've learned in a previous video when we talked about the atomic structure that the hydrogen atom has one proton in the nucleus. And since the proton is a positively charged particle, that means that the nucleus is positively charged. These nuclei spin on their own axis, and the spinning charge creates a magnetic field. So these nuclear spins act like tiny bar magnets, as you can see on the right. In the absence of an external magnetic field, the nuclear spins in a sample have random orientations. When we place the sample in an external magnetic field, such as that created by the superconducting magnets we use in NMR and MRI, the spins align with the external magnetic field, denoted as B0 and shown here by the purple arrow. The spins align either parallel or antiparallel with the external magnetic field. The spins that are parallel to the external magnetic field are at a lower energy, and the spin population at the lower energy is slightly higher than half. The spins that are antiparallel are at a higher energy, and the spin population at the higher energy is slightly lower than half. The higher the magnetic field, the higher the energy separation between the parallel spins and the antiparallel spins. Another important thing to know about nuclear spins in an external magnetic field is that besides the fact that they are aligned with the magnetic field, they also precess around the direction of the magnetic field with a frequency that is dependent on the magnetic field. This precession frequency is called Larmor frequency. This is similar to the precession of a spinning top. You can visualize the nuclear spin precession as the precession of the spinning top. You see the spinning top here precessing around the arrow representing the external magnetic field. Now it's time to remember that when we place the sample in the magnet, it is also inside another smaller coil, which I mentioned before can be used to send radio frequency pulses into the sample. And we've seen in a previous video how the radio portion of the electromagnetic spectrum is the electromagnetic radiation with the lowest energy. When we send radio frequency pulses to the sample, if the frequency of these pulses matches the Larmor frequency, so the energy of those pulses is equal to the energy difference between the parallel and the antiparallel state, then we have the phenomenon of resonance. Then we'll have a transition of a spin from the lower energy state to the higher energy state. This spin transition is then detected, and as the magnetization returns to equilibrium, the signal is detected by the coil and it is recorded as a free induction decay. This is the NMR signal as a function of time. And if we apply to this signal a mathematical transformation called a Fourier transform, we can transform the signal from the time domain to the frequency domain. Here we have peaks that appear at different frequencies, and this is called an NMR spectrum. But what exactly do we see in an NMR spectrum? These different peaks that we observe in a spectrum correspond to the resonance frequency of atoms in a sample, where the atoms have different local environments. These are atoms of the same type, let's say hydrogen atoms, in a molecule where the hydrogen atoms have different environments. Since the local environment for each hydrogen in a molecule could be different, this is reflected in the NMR spectrum by the frequency at which the peak corresponding to that atom appears. All the NMR spectra are referenced to the resonance frequency of the atoms in a reference sample whose resonance frequency is known. An example of reference sample is tetramethylsilane shown here, but there are other references that are used in NMR. And the resonance frequency of an atom in a sample with respect to that reference is called a chemical shift. And the units that are used are parts per million, or ppm. We can record these kinds of spectra for many other nuclei, not just hydrogens. Another one that is often used, especially for studying organic molecules, is carbon. But there are many other nuclei that are used in NMR. NMR has many applications, and they can vary from pharmaceuticals to energy materials to polymers, food, cosmetics, to biological research on proteins, DNA and RNA, and to the MRI applications of scanning the human body to acquire images inside the body. In cultural heritage, NMR can be used to study the materials that cultural heritage objects are made of. And it can also be used to study the degradation of objects of cultural heritage. After working for 15 years in NMR, I think I might be a little bit biased when I say this, but I think that NMR is one of the most useful scientific techniques that we have. If you liked learning about NMR, please give this video a thumbs up and let me know in the comments below which of the NMR applications that I mentioned you would like to learn more about. Today, we discussed the general principles of NMR, and in the next video, we will talk about mobile NMR and how mobile NMR can be used in cultural heritage. If you don't want to miss that video, hit the subscribe and the bell button to receive notifications every time I upload a new video. Thank you for watching, and I'll see you next time. Bye!
That's it for today. Thank you for watching. See you next time. Goodbye.